Oh man, that's a debate for something other than today. It's tough. It's I feel like Kobe and MJ were very similar to each other, at least in terms of style. But like I feel like LeBron is kind of different than all of them. I don't know if it's I know it's people like to debate that all the time, but I feel like it's hard to compare them because they did such different things. I will say that I don't have that many memories of watching prime MJ play. I was really young when MJ was in the league, so but I do have a lot of memories watching Kobe play, and of course, a lot of memories watching LeBron. So it's it's tough. I get it. I get it. I'll always have a soft spot for Kobe though, just because I was fortunate enough to be old enough to remember all of the titles that he won for the Lakers. So it's funny. I have one of my good friends that lives in New York, and like last year when the Lakers won the title, I was like, man, it's been so long. It's been so long since I've seen the Lakers win a title. I think, yeah, it's been just this is just the sixth one that I've seen. And then my friend was really upset just because he's never seen the Knicks win a title in his lifetime. MJ did do Space Jam. Man, I love Space Jam. You see the new trailer for LeBron Space Jam? What do you think? Yeah, and I think it's just because LeBron is such a yeah, that's true. Yeah, I think just also just the whole thing with I think LeBron's taking the got to save my son kind of thing too. So yeah, he's definitely a very different image than MJ had. Yeah, same here. Yeah, definitely gonna watch it too.
Hey, Professor.
Hey, how's it going?
Good. I meant to ask you last time. When you said you took your second dose, right?
Yep.
What were the symptoms of the second dose?
It's interesting. Like I didn't get as many symptoms as I think most people have. I think most people get like basically they almost get the flu when they get their second dose, and so they have like kind of chills and they have fevers. They just have no energy, things like that. And so my energy definitely went down. So today I'm feeling mostly better, but last couple of days I've been pretty just kind of just really tired. But I was feeling a little bit feverish on the day that I got the vaccine, but I haven't really gotten any chills or any flu-like symptoms. But that's generally what people get from the second dose.
Oh, okay. Because my mom, she was complaining that she was dying from
Yeah.
the first shot.
Oh,
So
yep.
she said she was getting like body aches, and I just got arm pain. That was all I got.
Oh, okay. Yeah. I got arm pain from the first one too. The arm pain from the second one wasn't as bad for me. But yeah, I think for most people, I think their second dose is worse. But for some people, their first dose is their second dose is not as bad as their first one. So that was the case for me. But I think I might have just been really fortunate in that sense.
And which vaccine did you take? Did you take the Pfizer or the Moderna or Johnson? Well,
I got the Pfizer one, and so
oh,
it just happened to be the one that was available at the site that I was going to. So I didn't pick it or the other one. It was just the first available appointment that I could make.
yeah.
Okay, so it's 5:30. So let's go ahead and get started today. All right. Good evening, everyone. How's everyone doing today? Good. I see a thumbs up. Scary face, or shocked emoji face, I should say. Um, so hopefully, today we don't have any technical difficulties. My iPad's still connected. It was really weird last time. It seemed to just sign me out of Zoom just kind of spontaneously last time, and I can't really figure out what's going on. But today, hopefully it'll be okay. For the last few lectures, it's been okay. So, we're gonna roll. Okay, so the plan for today is that we're going to finish up our lecture notes on diffusion with finite volumes. And so I think last time we got cut off basically when we were talking about 2D finite volume methods. Okay, and so we'll finish up, the theory behind that. I have a code that I want to show you guys, an example code that you can take a look at. And then from here, after today, I'm pretty confident that you should be able to do the homework. 5. I think that's posted onto Canvas right now. Right. So I think homework 5 is just it just has to do with just this diffusion with finite volume stuff. Okay. Okay. So any questions I can answer before we get started? Okay. All right. So if there's no questions, let's go ahead and get rolling. And what we were covering last time was 2D diffusion with finite volumes. All right. So compared to when we did 2D diffusion with finite differences, we are going to go a bit faster here, just because a lot of the same concepts back then still apply, right? And so if you remember from last time we did 2D diffusion, we spent quite a bit of time talking about kind of the programming itself, right? And so we talked about how do you label your grid, how do you keep track of the coordinates, how do you keep track of the IDs, how do you compute the ID numbers and things like that. So all of that's still going to be the same. And you'll see that you'll see that in the script that we'll go over later today too. Right? And so what I really want to focus on is how do we go from the governing equation, which was our diffusion equation. So let me go ahead and write that down for you just to kind of give you a reminder. Right? And so remember, in finite volumes, we like to express our equation in vector form. Right? And so instead of using the derivatives, we use these Greek hieroglyphics, I guess you could say. Right? Right. And so here we have the upside down triangle here. That's a nabla, right? So remember that represents kind of the partial derivatives in each direction. And so we have nabla dot the gradient of phi, right? And so basically we're taking the divergence of the gradient of phi. So that's one way you can get the diffusion term. And on the right-hand side, we have our source term. And remember, the way that we obtain our finite volume equations is that we integrate these over our finite volume cell. Okay. And so I'm not going to go through the whole, thing again, because that's kind of what we did last time. But I want to show you kind of where we left off. And so after we performed an integration and we performed our integration trick, so we performed our divergence theorem, we applied our trapezoidal theorem, trapezoidal rule, right? We ended up with the following expression, right? In particular, I want to focus on just the left-hand side of this equation here. Right, so just this side, okay? Because the right-hand side, that's very easy to integrate. That I'll show you kind of later on. And so once over here, what we wanted to evaluate was the line integral around our cell, right, of the gradient of phi dot product with n ds. Okay. And so in other words, we want to evaluate an integral going around the boundary of our cell, right? So here's our 2D cell, right? And so to evaluate this line integral, we're just going to trace around the boundaries over here, right? So in other words, we're going to integrate basically just like this. Right? And what that gives us is basically a flux integral on each of the different faces, right? And so since this square is kind of disjointed, and so it's usually hard for us to integrate and turn a sharp corner like that. What we did was we broke up this integral into 4 different sections, right? And so I'm going to use our compass directions. And so I'm going to label the faces north, south, east, and west, right? And what we found was that, after applying the integration and then performing the dot product, we end up with the following, right? And so we end up with a term on the east face, so partial phi partial x on the east face multiplied by delta y, right? Where delta y, remember, is this length right here, okay? And this length right here is delta x, right? Right, then we have the term on the north face, which is d phi dy on the north face, delta x. Okay. Then we're going to subtract d phi dx on the west face multiplied by delta y minus d phi dy on the south face delta x. Okay. And this is kind of where we left off from last time. And so now the goal is we need to work on this expression here and turn it into an algebraic expression. Right? And the way we're going to do that is we're going to replace all these derivative terms that I'm circling in orange here and replace them with a simple finite difference approximation. Okay. The big difference here is that, because you might be saying, what's the point of doing finite volumes if we're just going to use finite difference anyway? And that would be a fair criticism. But the difference here is that, this finite difference, we're only just using a first order finite difference, or a first derivative finite difference instead of a second derivative. Okay? In addition to having all those other nice properties of finite volumes that we talked about last time, right? Where we're each of these integrals here, we can interpret them as a flux or the transport of our material across the boundary of our cell, right? And so, remember, the nice thing about finite volumes is that it has a very nice kind of physical interpretation that correlates very well with control volume analysis in fluids. Okay. All right, and so on the next page, I'm gonna go over how we replace each of these expressions, plug them back in, and then we'll see how we the algebraic expression that results from this. Okay. All right, any questions on any of this so far? This is just kind of a review from last time. Okay. All right, so let's go ahead and replace all of these derivatives here. And remember, we want to put these in terms of the cell center values. Okay. Because remember, we're doing cell-centered finite volumes here. And so what that means is that we're solving for the solution variables at the centers of our cells, right? Let me draw this a little bit to the, actually, let me do this. Okay. So if we draw kind of a little bit of a D-pad here, right? And so let's say that we want to write out the equation for the cell in the center, right? And so let me highlight this in green, right? And so if that's the cell that we're interested in, right? So we'll call this phi sub c, like we always do. Right? In order to write those equations, we're going to need the values of phi at all of our neighboring cells, right? And so, and each of these cells, we're evaluating the phi values at the centers, right? So let me go ahead and label these. Right? And so on the right-hand side, we have phi sub e for the east neighbor. Then we have phi sub n for our north neighbor, phi sub w for our west side neighbor, and then phi sub s for our south side neighbor. Okay. But remember, the distance in between the cell centers vertically is going to be delta y, and the distance between the cell centers in the x direction is going to be delta x. Right. And so having this in mind, let's go ahead and replace all of our derivative expressions from the previous page according to the cell-centered values. Right? Okay. All right, so let's start with d phi dx on the east face, right? And so this is going to be the difference between phi sub e minus phi sub c, right? And so it's just going to be the difference in between the cell-centered values of the east neighbor and ourself, right? Divided by the distance in between them, which is delta x. All right, so next let's do d phi dy on the north face, right? And so on the north face, this is going to be phi sub n minus phi sub c divided by delta y, okay? All right, next we have d phi dx on the west face, right? And so the finite difference approximation for this is going to be phi sub c minus phi sub w divided by delta x, right? Notice how I've swapped these. So, for the east face, we have phi sub e first and phi c second. But for the west face, we reverse it because we always put the one on the right first, because these are all basically traditional forward difference equations. Right, and same thing for the south face. So for the south face, we have phi sub c minus phi sub s divided by delta y. Okay. All right. And so now that we have algebraic expressions for all the derivatives, let's go ahead and plug this in to our line integral from the previous page. And so if we plug all that in, we get minus k. I'm just rewriting the left-hand side just so that you kind of remember what it looks like. Okay. And so we plug all those things in, we get minus k times first we have, d phi dx on the east face, and so we have phi sub e minus phi sub c divided by delta x times delta y. Okay. Right. So this guy is the same as this guy. I should say this guy is the same as that one. Okay. And so all we did was replace for d phi dx at the east face. Okay. Next, we're going to do the north face, and so we have phi sub n minus phi sub c, all divided by delta y, multiplied by delta x. Okay. And so this guy is the same as this guy. Okay. Right. Subtracted from the next one, which is phi sub c minus phi sub w all over delta x times delta y. Okay. And of course, this is the same as this that we just plugged in. Okay. And then minus phi sub c minus phi sub s divided by delta y times delta x, where this is the same as that. Okay. All right, so we're close. And so now that we've replaced all those derivatives there, now we have an algebraic expression. Now we just kind of have to simplify this a little bit, okay? All right, any questions so far on how we got here? Okay. All right, and so I'm going to simplify this even more. And so I'm going to assume something that we usually do is that I'm going to assume that delta x and delta y are the same. Right? And so we basically have even grid spacing in both the x and the y direction. And so, for everything that we do in this class, that's going to be the case. Okay. And so if we assume delta x and delta y are the same, we can go ahead and cancel all these out. We can cancel them out and combine like terms, and then we end up with our simple kind of expression, which will look very familiar to us. Okay. All right. And so we cross out all those guys, and we combine like terms, and we get phi sub e plus phi sub n plus phi sub w plus phi sub s minus 4 phi sub c. Okay. Sure. Yep. All right, and so this is what we get, and you're right. It should look pretty damn familiar because this is basically what we got from our 2D finite difference diffusion, right? Or at least the coefficients look very same, right? So if you remember from our 2D diffusion finite difference, our coefficients were 1, 1, 1, 1, minus 4, right? Which makes sense because we're simulating the exact same phenomenon here, and so we're simulating diffusion. And so the algebraic equation that we get from either finite difference or finite volume should look very similar to each other. Okay. And so, for the interior nodes, often is the case that, for both finite difference and finite volumes, you should get very similar coefficients, right? Which makes sense because, it's the same equation underneath, right? And, if you're going to obtain an algebraic equation for this, you should get something that looks pretty similar. And so this is both, both reassuring and also disappointing and kind of at the same time. It's a very strange feeling that, that you might be feeling right now, but it's good. Okay. Remember, the big difference here is that we're solving these for the self-centered values instead of the values at the grid points. Okay. And so last thing that we need to do is we need to put this together with our right-hand side, right? And so remember, the right-hand side of our equation was our source term. Right? And so the source term, I saved it to last just because it's the easiest thing to do. And so all we're going to do is basically we're just going to do trapezoidal rule on it. So remember, our source term is q of x and y, okay? And then when we integrate this, we integrate it like that, right? So we perform a 2D integral. And so all we're going to do here is we're just going to evaluate this using trapezoidal rule. Right? Because if there's, one thing that we hate doing in this class, it's we hate doing calculus. And so we do tricks to kind of avoid us doing calculus, right? And so we don't solve the differential equations and we don't perform integrals because, we just don't like doing that here. We don't do that here. Okay. And so the trapezoidal rule, remember, the way that we do that is we take the integrand, which is just q of xy, okay, and then we evaluate that at the center of the cell. Okay, and so that's what xc and yc are, right? And then to this, we're going to multiply by delta x, delta y, where these guys together are the area of the cell. Okay, so remember, each cell is delta x wide and delta x wide and delta y tall, right? And so we take the product of delta x, delta y, that gives us the area, right? And just for simplification's sake, if we assume that delta x is equal to delta y is equal to delta, right? Then this just becomes delta squared. Okay. All right, and so that's the right-hand side of the equation. And so now let's put it all together. And so let's put it together what we have at the top here, and let's put together this guy. And what we have, and then what we'll get is our 2D finite volume equation for diffusion for all the interior cells. Okay. So we have minus k, okay, times phi e plus Vn plus Vw plus Vs minus 4 phi sub c, right, is equal to q of xc yc delta squared. Okay. Right, so this is 2D finite volume diffusion for interior cells. Okay. And so, very, 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 very familiar for what we have for finite differences. Okay. And so for the interior cells, we end up with very similar coefficients. But remember, one of the big differences with finite volumes is how we're going to apply the boundary conditions, right? Because we don't have any cells or any solution points that rest on the boundary itself. And so the way that we're going to apply our boundary conditions is we're going to modify our governing equations. Okay. And I'll show you how to do that on the next page. All right. So any questions on this? All right, question. So if this were 3D, we would have 2 more terms for that diffusion equation and a -6 instead of -4, or are there other factors to account? No, yeah, that's a good observation. So for 3D, yeah, so you would if your cell is a cube basically, then you have 6 neighbors, and so you would have a -6 there, and there would be two more extra terms of these guys, and so you would have north, south, east, and west, and then I guess above you and below you as well. Mm-hmm. Yeah, so it's actually kind of good, that we're going through the theory at least from this approach, because you can apply kind of the same thing for 3D, and this goes for finite differences as well. And then you can use exactly everything that we've done in the class and derive those equations. So you're fully equipped to do it in 3D, but your computer probably is not, because your computer would probably be upset with you. Actually, for 3D problems, actually, the biggest limiting factor for, running these codes is actually the solution of the matrix set of equations. So it's not about your computer in particular. It's all computers in general. And so the challenge, with these kind of computational methods, that you end up with just these ginormous matrix set of equations, right? And so even for our 2D problems, we end up with like, maybe 100,000 by 100,000 matrix, which is huge. And you can imagine in 3D, the problem gets even worse. And so you might end up with matrices that are like millions by like a million rows and a million columns. And so for 3D problems, and this is true for most commercial codes, they don't write out the entire they don't write out the entire matrix, because that seems kind of foolish to have, a 10 million by 10 million matrix, especially when, the vast majority of all of the entries in the matrix are zeros, right? And so if you've kind of noticed, for our 2D problems, and this holds true for any 2D problem. So you can look back at some of our previous activities, and if you actually looked at the left-hand side matrix, the vast majority of the entries are zeros, right? And so it's only maybe about like 2%, like 2%, 3%, even 1% of the terms are non-zero. And so, actually, bigger codes, they use a method called sparse matrices. And so it's basically a very memory efficient way to store these ginormous matrix systems. And so instead of storing like just a bajillion zeros, what you can say is, let me just store the entries that are non-zero, and then just let me keep track of where they're located on the matrix. And so that ends up being a huge savings in terms of memory and in terms of time. And it's a topic that I would love to get into in this class, because I think it's really interesting, but there's just kind of not a lot. There's just not enough time. But in case you were curious, in case you wanted to look it up on your own, look up sparse matrix theory, and then you'll see kind of how these codes are implemented in practice. Yeah, some are billions. Yeah, some problems are so huge that you'll have matrix systems that are billions by billions. And of course, there's no way that you can store billions of zeros, and so it's you almost have to use sparse matrices for that. Yep. All right, that's enough of an aside. So are there any questions on this before we go into boundary conditions? Okay. All right, so let's go over boundary conditions. And so, what we're going to go over is nothing new. And so we're going to follow basically the same thought process that we did for the 1D problems. It's just now that, we're in 2D. Right? So let's go over Dirichlet boundary conditions first. All right, so remember, Dirichlet boundary conditions, the way we define that is we specify or prescribe the solution variable on the boundary. Right? And so we have a situation. Let's say that we have a boundary condition on the west side. Right? So let's say that we have a situation like this. Okay. Where this is phi sub c, this is phi sub n, this is phi sub s, and this is phi sub e. Okay. But instead of having a west neighbor here, we have phi 0, where this phi 0 here is a prescribed Dirichlet value. All right. And so the way that we're going to account for this is we're going to modify the implementation of the finite difference for that west face. Okay. Okay. All right. And so normally, we have the situation like this. We have minus k times d phi dx on the east face, delta y, plus d phi dy on the north face, delta x, minus d phi dx on the west face, delta y, minus d phi dy south face, delta x. Okay. Right. And so, normally what we do for the interior nodes when we have neighbors on all sides, we can replace these derivatives with their finite difference approximations, just like we did on before, right? And so the only place where we can't do that is for this guy, because we don't have a west neighbor, okay? And so what we're going to do instead is we're going to replace this with a finite difference approximation that incorporates this prescribed Dirichlet value. Okay? And so instead of having phi sub c minus phi sub w, we're going to have phi sub c minus phi naught divided by delta x divided by 2, okay? Because remember, we're only moving a half distance between the cell center and the boundary, okay? Right. And so you can go ahead and plug that in, and as well as all the other neighboring values, and then what you end up with is the following. Right? So we have minus k minus k times phi sub e plus phi sub n plus phi sub s. Right? We don't have phi sub w anymore because it doesn't exist. Right? Right? And then we're going to subtract 5 times phi sub c. Right? And that 5 is there because we have this 2 from that half distance. Right? Okay. And then outside of this, what we have is minus 2k phi naught. Okay. Right. And then on the right-hand side, there's not much on the right, actually. Let me just write out what's on the right. Right. And on the right-hand side, we have q xc yc delta squared. Okay. All right. And so now all we have to do is that since this quantity right here with the phi sub naught, this is a known quantity, right? We can go ahead and move this to the right-hand side. Okay. All right. Any questions on this? Okay. All right. And so if we do that, let me go ahead and write out the expression for a boundary condition on the west face. Right? Oh, no phi n. Yeah, phi n's right here. Phi n is right here. Yep. Mm-hmm. Yep. And so we go ahead and simplify this expression, and then we get the following. So we have minus k phi sub e plus phi sub n plus phi sub s minus 5 phi c. Right, this is equal to q of xc yc delta squared plus 2k phi naught. Right, and so this is the case where we have one Dirichlet boundary condition on the west side. Okay. All right. Okay. And so for the 1D problems, I think I told you guys to kind of run through this this exercise for both boundaries just because there weren't that many. But for 2D simulations, we have a lot of cells that border the boundary. And so if you want to go through this for every single cell, it's be my guest, but it's going to take a long time, right? And so let's go ahead and draw some general trends from this so that we kind of know in general that if we're bordering a Dirichlet boundary condition, what we should do in general. Okay. All right. And so in particular, I want to draw your attention to this, and the fact that there's no phi w, right? And so when you have a Dirichlet boundary condition, you have to make the following 3 adjustments to your normal equations. Okay. All right. So 1, remove neighboring phi that was supposed to be on the boundary. I should say on the boundary side. Okay. And so in this example here, we had a boundary condition on the west side, and so we remove phi w, right? And because there's no west neighbor. Okay. 2, and for 2, we're going to take the coefficient in front of phi c and then reduce it by 1. And so before, in our base case, that was a -4. And so we decreased that to a -5. All right. And so third, we need to move the Dirichlet boundary condition to the right-hand side. Okay. And in particular, the Dirichlet term that we're going to add is a positive 2 times k times phi naught. Okay. And so don't forget the 2, and definitely don't forget the k, right? Because the k can either be positive or negative, and that's going to change the sign of what we have on that left-hand side. Okay. Okay. And so when we're applying the boundary condition, you need to make sure that you add that expression to the right. Okay. All right. So that's how we do Dirichlet boundary conditions. And so if you follow these rules right here, it actually becomes, fairly simple, right? And you'll see, how we can actually account for that in the code as well. Right? All right, so now let's look at Neumann boundary conditions. All right, and so for Neumann boundary conditions, remember, we're going to replace the entire flux term. Okay. All right, so let's do an example where we have a Neumann boundary condition on the south face. Let me draw my Tetris piece. Right, and so let's say here we have phi sub c. This is phi n for our north neighbor. This is phi w for our west neighbor, and phi e. Okay. Right. So on the south side, let's say that our derivative or our flux is going to be equal to gamma. Right. And so here, this is our Neumann BC. Okay. And so same thing that we did for the Dirichlet boundary condition. We're going to replace the derivative on the south face, but this time we're just going to replace the whole thing, and so we don't have to do any kind of weird finite difference here. Okay. And so before, what we have is minus k d phi dx east face delta y plus d phi dy north face delta x minus d phi dx west side delta y minus d phi dy south side delta x. Okay. All right. And so now what we're going to do is we're just going to replace this guy with gamma. Okay. And then everything else kind of proceeds in kind of the same way. Okay. And so once you do that, you'll end up with the expression that'll show on the next page. Okay. All right. So any questions on this? Okay. All right, and so if you plug that in and then you plug in all the finite difference approximations for all the other ones, you end up with the following. All right, so we have minus k phi sub e plus phi sub w plus phi sub n minus 3 phi sub c. Okay. is equal to q of xc yc delta squared minus k gamma delta. All right, and so that's our finite difference equation, our finite volume equation for a Neumann boundary condition. Okay. All right, and so just like we did for the Dirichlet boundary condition, I'm going to write out kind of the general things that you have to do for a Neumann BC. Okay, and so first thing, and so whenever you have a Neumann boundary condition on your on the side of your cell, first thing you should do is remove the neighbor where the boundary is. Right. And so in this case, we had a boundary condition on the south face, and so we're going to remove phi sub s. Oh, sure, I can go back. Okay. Yep. All right. And so first thing, remove the neighbor because it doesn't exist. Right. All right. Next thing we're going to do is we're going to take the coefficient in front of phi sub c and increase it by 1 this time. Okay. And so, in our base case for our interior cells, we had a -4 there. But if we increase that by 1, then it becomes -3. Okay. All right, and then lastly, we're going to move the Neumann term over to the right-hand side. And so the Neumann term here is k gamma delta. Okay. Okay. But here you have to be really careful about the sign, because the sign for that Neumann term is going to change depending on which face that you're looking at. Okay. And so you can see right now in this case we have a minus sign, and you put a minus sign there when the Neumann BC is on the south or the west face. Right. If the Neumann BC is on the north or the east face, we're going to use a positive sign. Right, so this is really important because if you don't do this, then you're going to have flux going out the wrong direction from your domain, which is not a good thing. All right, so any questions on this before we jump into an example? Point 2, yes. It is phi sub c. Yes. Mm-hmm. If you don't watch what the flux you were doing. That's one way to think about it. Yeah. Okay. So let's do an example then. And so I'm going to work out part of this example by hand, just because it's our first time seeing a 2D finite volume example, and so I want to make sure that we're all kind of on the same page for that. And then I'll show you the code that kind of implements this solution, because there are some finer points. Okay. And so let's take this 2D diffusion equation that we've worked with before, and then now let's solve for it in finite volumes. Okay? And so the equation is partial squared phi partial x squared plus partial squared phi partial y squared. Okay, this is equal to 3xy. Okay, and we want to solve for it on the following domain with the following boundary conditions. Right, and so on the left side, we have a Dirichlet boundary condition of phi is equal to 50. Then on the bottom, we have a Dirichlet boundary condition of phi is equal to 25. On the right, we have a Neumann boundary condition of 0, and so we have 0 flux there. And on the top, we have a another Neumann condition of 10. Okay. And then I'm going to break this grid into 16 cells. Right? Okay. All right. And so, I'll write out some of the equations by hand, and then we'll jump into the code from there. But before we do that, let's go ahead and identify our value of k here, and then our q value. Okay. And so in this case, our k value is -1, right? And then our q of x and y is equal to 3xy. Okay. So that's just going to be the right-hand side of this equation. Okay. And so knowing all these things and knowing how we're going to discretize it, we want to write out by hand what are the finite volume equations for solving this guy. Okay. All right. Any questions on that before we start writing out the equations? Okay. All right. And so let's start with kind of the general finite volume formula for our interior cells. All right, and so for interior cells, we get the following. So we have minus k times VE, plus Vn plus Vs plus Vw minus phi sub 4 times phi sub c. Okay, is equal to q of x c y c delta squared. Okay. And so we can just go ahead and directly apply this equation to every finite volume cell that has 4 neighbors, right? And so basically, for all of the ones on the interior. And so, I'm not going to do that because, I know you guys can kind of plug in the numbers for that one. Okay. And so what I want to do is I want to give you some examples for how to make the modifications for the boundary cells. Okay. And so in particular, I want to do a couple of the corners because the corners are really interesting because the corners have 2 boundaries on them. Right. And so, this is kind of one of the big differences where when finite differences, remember, we just ignored the corners. Like we didn't really care what they were doing. But here, we can't avoid the corners because remember, we're solving for them at the cell centers. And so, what you'll see is that for the corner cells, we're going to need to apply our Dirichlet or Neumann boundary condition procedure twice. Okay. All right. And so let's start with let's start with the cell that's not on a corner, just so that we can kind of see what's going on. So let's start with cell 2. And so cell 2 is this guy right here, right? And so you can see that cell 2 has 3 neighbors, and so it has a neighbor on the west side, on the east side, and on the north side, but it has no south side neighbor, right? And so in particular, we have a Dirichlet boundary condition on the south. Okay. All right. And so if we apply our equation, and remember, for Dirichlet boundary conditions, we take this -4 and we subtract 1, and so it becomes -5. We remove phi s from the equation. Okay. So we're going to remove phi s. Okay. Turn -4 phi c into -5 phi c. Okay. And then we're going to move that Dirichlet boundary condition to the right-hand side. Okay. And so let's go ahead and do that. And so we have minus k, but in this case, minus k is just -1. Okay. And so we have -1. Okay. And so that's on the outside. Then we have phi sub e, and phi sub e is our east neighbor. And so the east neighbor for cell 2 is going to be cell 3. Okay. Then we have the north neighbor for cell 2. And so the neighbor that's directly, the cell that's directly above cell 2 is going to be phi 6. Right? Okay. We don't have a south neighbor, and so we're not going to worry about that. But we do have a west neighbor. And so our west neighbor is going to be phi 1. Right? Okay. And then we have -5 phi 2, which is phi sub c. Right? Right, so I'm not going to plug in the x and y coordinates, but you can go ahead and do that. Okay. And then to this, we're going to add 2 times k times phi naught, right? Or in other words, 2 times our diffusion coefficient times our Dirichlet boundary condition value, right? And so in this case, our k value is -1, and then our Dirichlet boundary condition value is 25. And of course, this needs to be simplified a bit more, so we can go ahead and cross these guys out and make this a -50. But that's essentially how you make those changes for that. Okay. All right. So any questions on this? Okay. All right. So now let's do one of the corner cells, because the corner cells are pretty interesting. And so I'm going to do cell 1, which is in the corner, bottom left corner, and I'm going to do cell 4 as well, which is the bottom right. Okay. All right. So first, let's do cell 1. And so cell 1 is in the bottom left of our domain, right? And so we have a boundary condition both on its west face and on its south face. Okay. And in this particular case, we have both of them are Dirichlet boundary conditions. Okay. Okay. And so we're going to apply our recipe for Dirichlet boundary conditions twice. And so we're going to remove both of those neighbors. And so we're going to have no phi w and no phi s, right? And then we're going to reduce the coefficient in front of phi sub c by 2 this time, right? Since we've applied 2 boundary conditions, and we're going to move 2 boundary condition terms to the right. Okay. And so in the end, what you get is phi sub 2 plus phi sub 5, right, minus 6 phi 1, okay? Okay, so this phi sub 2 here, this was our phi e, right? So that's our east neighbor. This phi sub 5 here is phi n, or our north neighbor. Okay. And then notice here we have minus 6 because we have minus 5, minus 1, right? And on the right-hand side, we have 3 xi, yj, where of course you would plug in the x and y coordinates for the cell, okay? And we have 2 boundary conditions here, right? And so we have 2 plus 2 times minus 1 times 25, which is the Dirichlet boundary condition on the south side of this of the cell. And we have plus 2 times minus 1 times 50, which is the boundary condition on the left side of the cell. Okay. Okay. And there's our equation. Okay. Right. So you have to be careful with the corner cells, because the corner cells you have to apply things twice. Right. And I'll show you how we do this in code, where it kind of it kind of does this automatically for us. All right. And so one more example, just to kind of really drive the point home. Let's do cell 4. And so cell 4 is in the corner as well, right? And we have 2 boundary conditions here, but this time we have a Dirichlet boundary condition on the south, but a Neumann boundary condition on the east. And so even though we have a mixed boundary condition situation here, we can just do kind of exactly the same thing as we have been, just apply it twice, right? And so first thing, we're going to take the south neighbor and the east neighbor and just eliminate them from the equation, just because they don't exist, okay? And so we're only going to do this for the west neighbor and the north neighbor. Okay? And so the west neighbor for cell 4 is going to be phi 3. The north neighbor is going to be phi 8. For the coefficient in front of phi sub 4, first we're going to subtract 1 for the Dirichlet boundary condition. Then we're going to add that 1 back for the Neumann one. So in the end, we just end up with minus 4. Okay. Then from there, we're going to add the Dirichlet boundary condition. Okay. So the Dirichlet boundary condition is 2 times 25. Then we need to incorporate the Neumann BC, right? And so the Neumann BC in this case is on the east face. And so we need to remember, we need to apply the Neumann BC with the correct sign, right? And since we're on the east face, we need to use a positive plus here. Okay. So we're gonna have a plus minus 1 times the Neumann value, which is 0, times delta. And since the Neumann boundary condition is 0, then this just kind of cancels out on its own. Okay. All right. And so that's kind of the procedure that you would need to do to derive these equations by hand, right? So for problem 2 on the homework, this is kind of the thought process that you would go through to solve for that. Okay. All right. So any questions on this before we jump into the Matlab code? Okay. All right, so let me go ahead and start sharing my screen. All right. And then here is the Matlab code. So let me go ahead and maximize this. All right, and so this is the Matlab code called 2D Diffusion Fvm, right? And so this is you should have this code. It should be in the on the Canvas site, and so you can download it and follow along if you want. Okay. And you'll see that the format for this code is very similar, or at least, the sections are similar to what we've done in the past, right? And so in the first section here, we're just defining all of the parameters. And so, we're defining the length of the domain, how many cells that we want to have, the grid spacing, the total number of cells, and all that stuff, right? And I also have a parameter here for the diffusion coefficient, okay? And so all that's, very standard stuff. But where things are different here is going to be in section 2, okay? So this should be different, right? And so section 2, this is where all the finite volume stuff is going to happen, right? But we start out with a nested for loop, right? And so first thing we need to do for any kind of situation like this, finite difference, finite volume, is we need to visit all the cells in our grid. Okay? And so this for loop, what it's going to do is going to visit every cell in our grid. Okay. And so remember, for when we did finite difference equations in 2D, we wrote the for loop to visit every single grid point in our grid. But now, since we're doing finite volumes, we have to visit every single cell, okay? And so we're gonna have one loop, I, that loops over all of the X direction, and another loop, J, which loops over the Y direction, okay? All right, and so that's the loop, and that's kind of why we do that, okay? Next thing we need to do is we need to compute ID numbers, right? And so, hopefully this should look very familiar to you, but just because we're in finite volumes, we're going to use the exact same scheme that we used before to number all of the cells, okay? And so, we're going to use this equation here where we have nx times j minus 1 plus I, right? And so that gives us the ID number for our cell in question, right? And then we're going to modify this equation for the east, the west, the east, the north, and the south, right? Adjusting the values of I and j accordingly. Okay, and so all this is standard for 2D stuff, and so we've all kind of done this before. Right? All right, and so all the new stuff is actually going to be in these two if statements right here, right? And so let me kind of explain what these are, right? All right, and so what I've done here is you can see that I have kind of two big if statements. So I have this first one that I'm highlighting here, and then I have the second one that I'm highlighting here. Right? And so what you can think of this is I'm basically evaluating the east and west terms of our finite volume expression at the same time, right? And these if statements are here to basically ask if we're on one of the boundaries. Okay. All right, so let's look at this first statement first, right? And so first we check if I is equal to 1, right? And so basically, if I is equal to 1, remember that tells us that we're on the very left side of our domain, okay? And so that's what we have here on the west boundary. Right? And so if we're on the left side of our domain, that means we're bordering the left side of the boundary, which means that we need to apply our boundary conditions here. Right? And so that's what I have here for the comments that said, for the west boundary, apply the Dirichlet boundary condition. Okay. All right. And so normally what we do is we, for the base case, if we're evaluating both the east and the west terms at the same time, we're going to add a positive 2 to that diagonal term, right? You can see here I've added because, I basically took the minus sign in front of k. Let me pull that up again. Right? I've taken this minus sign here, and I've kind of distributed this minus sign throughout, and so this minus becomes a positive here. And so for the east and west terms, for the base case, if we have a neighbor on the east and the west side, then we're going to add a plus 2 times minus k times k here. Okay, and then we're going to subtract the k from both the west neighbor and the east neighbor. Okay, and so that's basically. That's basically, this east term right here and this west term. And so that's what I'm kind of distributing in through here, which is this minus k. Let me kind of keep this off to the side right here. All right. Okay. And so that's what you have. That's what you see here for this plus 2k and the minus k for the west and the minus k for the east. Okay. And so if we have a Dirichlet boundary condition, remember what we do is we take this this number here and then we decrease it by 1, right? And so that's what I'm doing here by changing that minus that plus 2 to a plus 3. Okay. And then of course, since we don't have a west neighbor here, then we're going to eliminate this this line of code. And so we don't have to implement anything for the west ID, okay? But we do have to implement something for the east ID. Okay? And then on the right-hand side, what we have to do is we have to modify it in order to account for that Dirichlet boundary condition. So we add a +2 times k times 50 here. Okay. All right. And so that's handling the west side of this cell, right? And so for any cell that borders the west of the boundary, we're able to deal with it here, where we make the appropriate adjustment to the diagonal term. We eliminate one of the neighbors, and we add the the component to the right hand side, right? And so all three steps that we just went over for how to apply boundary condition, you can see it implemented in the code right here. Okay, so any questions on this so far? Okay. All right, and so that's the west boundary. Okay, and now let's do the east boundary now. And so the east boundary happens when I is equal to nx, right? And so basically we're on the very right side of the domain. That's why we have I is equal to nx. Okay? And so here we have a Neumann boundary, and so we need to apply our methodology for applying the Neumann boundary condition terms. Okay. All right. So first thing we do is that instead of a 2k right here, we're going to reduce the magnitude of this by 1. Okay. And sort of instead of 2k, we're just going to add just 1k here. Okay. And that's what you see in this comment right here. So adding 1k for the Neumann boundary condition. Okay. And then for the west ID here, we're subtracting a k, because that's what's normal here. But we don't have anything for the east term, right? Because remember, for the whenever we have a boundary condition on a boundary, we eliminate that term from our equation, and so we don't have to do anything for the east side here. Okay. All right, and the last thing we're going to do is we're going to add the Neumann boundary condition term to the right-hand side of the equation, and so that's going to be a positive k times 0, since we have a Neumann condition of 0 on that east side. Okay, multiplied by dy. Remember, we use a plus side here because we're on the east side of this boundary. Okay. Okay. And so that's this first if statement. So that takes care of the west and the east boundary conditions, as well as the west and east neighbors if we have them. Then if you look at this line, these lines of code right here, we basically have the same thing for the north and south. Right? And so for north and south, we're checking values of j. All right, and so if j is equal to 1, that tells us we're on the south boundary, and on the south boundary we have a Dirichlet boundary condition of 25, right? And so you'll see basically the exact same modification to the code here as I did up here, right? And so for this, since we have a Dirichlet boundary condition, we subtract 1k from the diagonal term, right? And so that's a phi sub c, right? And then we eliminate, the neighboring cell, which is for the south face. And so that's why we only have an equation here for the north, right? And then we add the corresponding contribution to the right-hand side, which is a 2 times k times 25, right? Okay. And so for the north side, we do, pretty much the same thing. And so first thing we do is we adjust the value of the diagonal term, or the phi sub c term. Okay. So here we add 1k to the phi sub c term, right? And so from here, we only make the adjustments for the south neighbor, right? Because we don't have a north neighbor if we're on the north boundary, and then we make the appropriate adjustments to the right-hand side where we add the Neumann boundary condition there. Okay, and so here you see we have a positive k times 10 times dx. And then here we finally have our base case where, if we have both a north neighbor and a south neighbor, then we know what to do. And so we add a 2k to the diagonal term for phi sub c, and then we subtract k from the south and the north. Okay. All right. And so that's all the left-hand side. And so last thing we need to do here is we need to apply the forcing function, right? And so for the forcing function, first thing we have to do is we have to compute the coordinates of the cell centers. Okay. Okay. And so I called these variables x pos and y pos, right? And so x pos is going to be 0.5 times dx plus I minus 1 times dx, right? And you'll notice here that, I added this guy right here, the 0.5 times dx, because remember, we want the coordinates of the cell centers, okay? And so we don't want the coordinates of the grid points anymore. And so we want the coordinates of those cell centers. And so that's kind of why we have this, okay? So we have the 0.5 times dx and the 0.5 times dy. And then to that, once we compute that, then we add the forcing function to the right-hand side. And so that's 3 times x pos times y pos times dx times dy. Okay, so any questions on any of this so far? Okay. All right, and so at this point, both the left-hand side matrix and the right-hand side vector are done solving. And so from here, all we just have to do is just invert the solution, right? As we just do our classic A / B, right? And so from there, and so I have this here just so I can time it. And so let's go ahead and run this code. And so it's going to take a little bit of time because I have it be 100 by 100 right now. Okay. And here is our solution, right? And so you can see from our solution here that we have a boundary condition of 25 on the bottom. And so you can check that from the colors here. And on the left-hand side here, we have our Dirichlet condition of 50. And then, everywhere else we have our boundary conditions. All right, and so that's basically a 2D finite volume code, right? And so, the big differences that you'll see here is that, inside this loop right here, I handle everything at the same time, right? So if you kind of compare this to our finite difference codes, and kind of the reason the numbering is messed up is because, from finite difference, what we did was we handled the boundary conditions outside of the main loop. But for finite volumes, just because of the way the equations are formulated, you can handle all of the boundary conditions and, all the interior nodes within the same loop, right? And so in that sense, in terms of coding, finite volumes can be a little bit more compact than finite differences. And if you look at it from the perspective that you're handling basically one integral at a time, it's kind of very elegant in that sense where, we can handle basically every integral for every cell kind of within the same loop, just with some if statements, okay? All right. Right, so that's all I had planned for today. And so the next topic that we're going to go over is how to do convection problems with finite volumes, okay? And so we're kind of basically following the same path that we did for finite differences, but with finite volumes now, okay? And so the next thing is convection. And so, all the same things that you remembered from convection in the past, it's going to apply here. It's just that now we're going to do it in the finite volume context, okay? All right, so that's all we got planned for today. And so I don't really want to start a new thing in the last 4 minutes. And so I'll call it just a bit early. And so thank you guys for tuning in today. You should be fully equipped now to do the homework. So definitely get started on that. And if you have any questions on the homework, definitely let me know, and I'm always happy to answer. So have a great evening, guys. Have a great weekend, and I'll see you guys on Monday.
Thanks, Professor.
Thanks, guys. All right, so after the convection lecture, after the convection lecture, you should be able to do most of the project in terms of finite volumes. We do have to cover how to do unsteadiness in finite volumes, and so that's going to be one of the last things that we cover in this class. But you should be able to do kind of most of it. The unsteadiness for finite volumes is actually almost exactly the same as in finite differences, and so you can apply just basically the same methodologies as we did from before. Yeah. Yeah, I think probably by next week I'll have written the starter code for finite volume too. So for those of you who want to do finite volumes, or for the grad students, I think then that'll be helpful for you guys. So I'll put together the starter code for next week. Yeah. If you want to ask me about your 410 project, I'm happy to answer that as well.
Can I share my screen with you real quick?
Yes, actually, let me stop the